time we're going to look at a case study of agri-environmental management in Australia, and the example is the Gippsland Lakes, which is a system of coastal lagoons located in southeastern Australia. The tricky thing about these lakes is that there are 7 rivers that drain into the 3 main lakes, and they deliver water pollution problems of various types into the lakes, which is what we'll be talking about. The lakes are located here on the map, east of the city of Melbourne. And they're environmentally important for a variety of reasons. They're a key environmental asset in the Australian state of Victoria, and they're also subject to international environmental agreements, such as being listed under the Ramsar Convention, the Japan-Australia Migratory Bird Agreement, and the China-Australia Migratory Bird Agreement. In addition, they're of some economic importance. They're a major destination for tourism, and tourism in the region generates about $250 million per year. The watershed, or the catchment around the lakes, is important for agriculture. There is production of around $1.3 billion per year from agriculture in the watershed, and there's a variety of different types of agricultural system in that catchment area. There's dryland grazing, there's irrigated dairy, there's dryland dairy, and there's horticultural cropping. So the issue, as I've hinted, is that agriculture in the area has led to nutrients and sediment entering the lakes and reducing the water quality through eutrophication and sedimentation. And this has negative impacts on financial, social and environmental values associated with the lakes. National and state governments have agreed that there is a need to find ways to try and deal with this problem, to reduce nutrients and sediments getting into the lakes. But the problem is that there's a huge number of possible ways of achieving this, and it's difficult to decide what's the best strategy. They have adopted an official goal of reducing nutrients by 40%, but that still leaves the question of how can this best be achieved? And does this 40% target offer the best value for money? Are there other targets that would actually be better? There are many, as I've said, there are many different management options that could be encouraged or promoted. In the dryland dairy, mixed dairy beef farming system, there's options for reducing effluent or effluent management, and for drainage line or riparian vegetation buffering or fencing to protect those areas. In the dryland beef sheep area, a key option is to keep groundwater cover above 70% to reduce hill slope erosion. There's also a strategy of repairing gully and tunnel erosion, and of drainage line or riparian buffering or management fencing again. For the irrigated dairy area, one of the good options is on-farm reuse systems for tailwater, particularly on heavy soils, conversion to pressurised irrigation on the light soils, automation of irrigation on light soils, effluent management and drainage line management again. And in some of the forestry areas, one of the strategies is to improve the roads so that there's a reduction in runoff and soil erosion. So I was involved in a study that tried to evaluate these options, and one of the things that we did as part of that study was to develop a spreadsheet tool so that we could efficiently do benefit cost analysis of a big variety of different strategies. The objective of the analysis was to determine which management options in which farming industries offer the cheapest way to achieve particular environmental targets. The 40% target was one of them, but we looked at others as well. And then we looked at what is the most that can be achieved in the way of pollution reduction with a particular budget. So, very briefly, some of the results of this study. This table shows 4 different targets for pollution reduction. We looked at a 40% reduction, which is the official target, 30%, 20% and 10% reductions. And you can see that there's a very strong relationship between the strength of the pollution reduction target and the cost of achieving those targets. So you can see high initial costs for a 40% reduction and much lower initial costs for only a 10% reduction. And in fact, the relationship between the pollution reduction target and the cost of achieving it is highly nonlinear. The costs increase at an increasing rate as you go to more ambitious pollution reduction targets. And that's one of the main reasons why in the last column you can see the benefit-cost ratios. So the most ambitious target of a 40% reduction has a very low benefit-cost ratio, whereas the least ambitious target of only a 10% reduction has a much higher benefit-cost ratio. So how should we interpret these results? So each of these solutions involves a particular set of farming changes that achieves the target at least cost. So that information itself is very interesting, very useful to environmental managers because it indicates which of the changes they should be promoting. The other result that I've already touched on is that the official target of a 40% reduction in nutrients is not a cost-effective option. The expected benefits that would result from that target are far less than the costs. And targets of 20 or 10% reduction would result in benefits equaling or exceeding the costs. So they look more attractive. So in summary, the Gippsland Lakes has high environmental and tourism values, but agricultural activity in the region has elevated nutrient levels within the lakes, causing problems from eutrophication and sedimentation. Benefit cost analysis allows us to investigate a wide range of management options that we could use to try and reduce these problems of pollution, and allows us to identify the options that give the best value for money.